Hey everyone, today we will be implementing the HIFIGAN architecture. It is a type of a neural vocoder. The main prerequisite to this is the Tacotron video. So we're going to be using some bits and pieces of the code from that original Tacotron video from a while back. I'll link it down below. And I hope you're also comfortable with just general audio processing. I'll also link my video down below for that. So let's quickly talk about what neural vocoders are and what's changed. So a neural vocoder is something that takes, in this case, some intermediate representation, in this case a spectrogram, a Mel Spectrogram, and converts it to audio. So let's remind ourselves a little bit of what we did in that Tacotron video. In Tacotron, we wrote an architecture that can take some input text and then produce a spectrogram. What we didn't implement is this part right here, the WaveNet model. The WaveNet which basically takes a spectrogram and produces the waveform. The reason we didn't do this is because WaveNet's a little bit old now, and more typically today we use the HIFIGAN or other architectures, but HIFIGAN is one of the most popular, which is why we're going to be covering that. So the Mel Spectrogram, remember, is basically a image representation of the audio. What it tells us is we have the time axis and the frequency axis, and it tells us how much energy is there at different frequencies at different time steps. It's essentially just a short time Fourier transform, if you're familiar with those, but it's scaled from frequency bins to Mel bins because Mel spectrograms are a better representation of human hearing, human perception, the way we perceive audio and pitch compared to just standard spectrograms, right? So that is our goal today, essentially and let's keep this right here. Yeah, so our goal today is basically to implement something that can take the spectrogram and produce our WaveNet, right? Produce a waveform from it. Now we did talk about we talked about the Griffin-Lim algorithm. So the reason this is a challenging problem to go from spectrogram to waveform is because, well, if this is just basically a short time Fourier transform, why not just do the inverse short time Fourier transform? We'd be happy. The problem is the inverse short time Fourier transform requires both the magnitude and the phase component. Remember, when you do Fourier transforms, there's magnitudes and phases. They're complex numbers, right? So you have the magnitude of it and the angle as well. But the Mel spectrogram here is a magnitude only image, right? There's only magnitude information here. This neural network only predicts the magnitude, the amount of energy at every single time step. And so if we only have the magnitude information, there's no way to just use inverse short time Fourier transform and produce our waveform, right? That's basically the problem. And the Griffin-Lim algorithm is an iterative approximation method. It iteratively approximates the phase information, the missing phase information, by basically saying, well, I don't really know what the phase information is, so why not just initialize it randomly and then just basically take that and do the inverse Fourier transform and then do the Fourier transform and then adjust inverse Fourier adjust. It's an iterative algorithm. I don't want to go into too much detail. But that's the main idea. The Griffin-Lim algorithm can take a magnitude spectrogram and produce audio. The problem is it may produce audio, but the audio quality is a little bit of question. So let's kind of take a listen here. I have open. Oh, I guess I don't have open. Let me just reopen it. Here we go. So this is what we're going to be building up to, right? So this will be what we're going to be essentially implementing, to be able to do this. But let's just skip to the end just to hear what it sounds like. So what we're doing here is we're grabbing from the LJ speech dataset. So we're still working on the single speaker LJ speech dataset. I grab an audio file and its corresponding transcript, and I use this audio to Mel conversion. This is a chunk of code that we're going to be reusing from our Tacotron. So I go ahead, I take the audio file, the waveform, and I create this Mel spectrogram, right? So this is the Mel spectrogram that represents the audio, right? So basically at the different frequency bins, how much energy is there at different frequencies at different time steps? And you kind of get these cool, like you can see harmonics and things like that, and that's awesome. So what we want to do is invert this. Okay, no problem. Let's use the Griffin-Lim algorithm, and let's just take a listen.
He had been in the employ of a corn chandler at Islington, and went into London with his master's cart and horse.
Okay, so that sounds good. It's saying what we have here. Right? He had been in the employ of a corn chandler at Islington and went into London with his master's cart and horse. So it is saying this, but the audio quality is definitely not that good. It sounds robotic. You can hear kind of like this, like tremoring in it. It's just not that good. What we want is something like this. This is the HIFIGAN architecture.
He had been in the employ of a corn chandler at Islington and went into London with his master's cart and horse.
Okay, so it's not perfect, but this
He had been in the employ of
is way better than
He had been in the employ of a corn chandler.
right, and that's basically what our goal is for this video. Creating a neural architecture that does what Griffin-Lim does. Griffin-Lim takes Mel Spectrograms, magnitude Mel Spectrograms, and produces audio. Well, we're going to train a neural network to do exactly the same thing. The HIFIGAN architecture looks like this. It takes a Mel Spectrogram, and it uses two different types of GANs, the multi-period discriminator and the multi-scale discriminator. We'll be digging into the details of this as we go. This is essentially an iterative method on the original MelGAN architecture. The MelGAN architecture essentially had exactly the same generator and had essentially the same multi-scale discriminator, but the HIFIGAN added this new multi-period discriminator. That's the main novelty for what we're going for here. So to do all of this, like I mentioned, there's going to be some code that we're going to reuse from earlier, from that Tacotron video. And we'll refer to bits and pieces of the paper as we're going. But for now, let's just stick to this. So from the Tacotron video, we're going to be reusing a couple of these methods. Not all, most of them don't matter too much in terms of implementation. The details are pretty easy. So I'm going to quickly go through these and just spend some time explaining the audio Mel conversions. If you already saw the Tacotron video, you can go ahead and just skip this, right? So as a quick recap, we have a method to load waveforms, basically just load a waveform at some sampling rate, no problem there. We have a method to take amplitude and convert to decibels. And decibels is essentially just a log transform, right? It's 20 times log base 10 of our, our original data. It's just a standard log transformation formula. And we set a min decibel, just so we don't have a value like -1000 or -10,000, because it is a log scaling. And so just so we don't have that, we're going to go ahead and just make sure we clip our data to be no decibel less than -100, because after that, it's not really perceivable anyway, but there's always like numerical things, right? Numerical precision issues that we could fall into. So we just make sure we clip it this way. After that, we have a decibel to amplitude. So if we're going to convert from amplitude to decibel, which is 20 log 10, then if you do 20 times log 10 of a value, well, if we divide by 20 and then do 10 to the power, that'll get us back, right? It's just the inverse, essentially. We have a normalization. So when we do this transformation, our original data, which has a when we convert to decibels, it'll be between like -100 and like 2 or something like that, right? That's kind of the range of the data X. That's not all that helpful to us because neural networks like things that are centered at 0 and between like -1 and 1 or -3 and 3 or whatever. The implementation that I was following, they were doing between -4 and 4. I'm like, okay, sure, we'll just do -4 and 4. We could have also done -1 and 1. I don't think it would have made any difference. So there we go. So we're just taking this and rescaling something between -100 and something, the original data, what the decibels produce, to something that's between -4 and 4. Denormalizing is exactly the same thing, but it takes something between -4 and 4 and just puts it back into the original unscaled version. That's all. And we also have this pad for Mel, which I'll talk about in just a second when we use it. Our audio Mel conversions was a method we wrote that had two important things. Something that can take an audio file and convert it to a Mel spectrogram, and something that can take a Mel spectrogram and convert to audio. And this method is exactly the problem that we want to solve because Mel to audio requires that not as ideal Griffin-Lim algorithm. So to convert something from audio to Mel, it's pretty easy. We get our audio, make sure it's a tensor. We do a short time Fourier transform, which is just a standard STFT. But like I mentioned, short time Fourier transform is good in that it represents the amount of frequency magnitude. The magnitude is the different frequencies at the different time steps. So that's good, but it's not really a representation of how humans perceive pitch, right? So in my audio processing video, we talked about that there. So Mel spectrogram is closer to how humans perceive the differences in pitch. That's why we like Mel spectrograms. So what we do is we take the spectrogram. This returns a complex number. We don't really care about the phase information like we've talked about, at least for this architecture. So we do torch.abs and that'll just grab the magnitude. So now we have the magnitude spectrogram. Now what we do is we take the spectrogram and convert it to a Mel spectrogram, which if you remember in labrosa.filters.mel, the conversion to a Mel spectrogram is simply just a projection. So in our case, what we have is a window size, or let's say n FFT of 1024. So that means we'll be processing 1024 samples, but of the 1024, only 512 of them will be valid because we're going to have positive frequencies and then their corresponding complex conjugates, right? The negative frequencies. We don't really care about negative frequencies as they're just reflections of each other. So we'll have 512 things here. From the 512 frequency bins, and they're linearly spaced out frequency bins, we're going to project them to 80 Mel bins. And Mel bins are, again, it's kind of like it's more like a log scale or something like that is maybe the best way to describe it. But it just essentially shifts and scales our original 512 frequency bins to 80 Mel bins. And these 80 Mel bins are just better representation of human pitch, right? Going and when I say human pitch, the idea is like if we go from 200 hertz to 400 hertz in human hearing, that's a double. But then when we go from 400 hertz to 600 hertz, we had the same delta. We increased by 200 hertz, but we don't perceive it as double. And that the discrepancy between the absolute difference and how we hear the difference in pitch doesn't really match. And that's what the Mel Spectrograms solve. And this is just a projection, right? It's just a simple matrix multiplication right here. It's a projection that takes in basically 512 samples and projects to 80 samples, 80 Mel bins. Okay, so this is standard basically 512 by 80 matrix, whatever it may be. And then we essentially map mol it with our spectrogram and we go ahead and we have so in this case, it'll actually be 80 by 512. This is 512 by number of time steps. And so we'll have with the 80 by number of time steps final spectrogram. We can then go ahead, take this Mel spectrogram, convert it to decibel, no problem. And if we want to normalize it between -4 and 4, which is typical what we want to do, then we're going to go ahead and normalize it as well and return it. To do from Mel to audio, to go back, just undo these steps. So if we normalize, then we have to denormalize. If we went from amplitude to decibel, we have to go from decibel to amplitude. If we, because we did a map mol with spectrogram, we need to invert that map mol. And this is where it gets a little bit complicated and one main point of weakness for the Griffin-Lim algorithm, because Griffin-Lim expects a spectrogram, not a Mel spectrogram. So the problem here is we need to invert this operation. Well, that shouldn't be much of an issue, right? If our Mel, right, if Mel is just equal to our Mel, I'm going to call this Mel A, like the projection matrix. So we'll call it Mel P, Mel projection at spectrogram, then our spectrogram, right, spectrogram should be equal to Mel P inverse at Mel, right? Just take the inverse, no problem there. The problem actually is that this Mel projection matrix is not square. It doesn't have to be square, and typically it isn't, because we have 512 in one dimension and 80 in the other dimension. And non-square matrices cannot be just inverted directly. So we have to use a pseudo-inverse, PINV, and pseudo-inverses will have some loss in information, right? It's not a perfect inversion. So some information is lost in this step right here alone. And then the Griffin-Lim is just a iterative approximation of the missing phase information. It's not going to exactly get it, but it'll get close. But we heard that the results are just not that convincing. And then we just take the data, audio. Once we use Griffin-Lim to undo it, we scale it back to int16 and return it, and that's it. So that's the main Mel to audio method that we used last time in the Tacotron implementation. But of course, we want to do better, and that's what the HIFIGAN will be for. We don't really care about the TTS dataset and collator. These were needed for training that Tacotron architecture, and it'll be needed for a quick inference thing that we'll need today, but we're not going to be really using this in any meaningful way. So we're going to ignore the details, and I'll leave it to you to just go watch the other video if you want to understand more about this stuff. Because again, we're going to focus on the HIFIGAN today. So what we need is a dataset. So let's quickly pull up the, let me pull up the figure real quick. In HIFIGAN, what we have is Mel spectrograms, and there's two ways we can do this. In the pre-training stage 1, we're going to take audio and we're going to we'll just compute their spectrogram, and then the model gets the spectrogram and tries to reconstruct the audio. That's pre-training. During fine-tuning, of course, we don't really care about these spectrograms as much. What we care about are the spectrograms produced by Tacotron 2. Because Tacotron will autoregressively, right, in the way that it's in the way that it's set up, it will produce a spectrogram, and these spectrograms should be close to the original ones because that's what we trained it to do. But there's always going to be some error, some approximation, something missing, some information gone, some domain gap, some distribution shift, something that's missing. And so the pre-training stage is just train the model that can take raw spectrograms and produce audio. The fine-tuning stage is train it on spectrograms actually produced by the model we care about, and then to the audio, right? So this will be the quick fine-tuning stage afterwards. But for now, we're going to be focusing on this. One thing to keep in mind is when we produce these spectrograms to pass into our model, they will be very, very, very short. Like we're talking about half a second or less of audio. The reason is we want our discriminators to be able to look at very fine detail in the generation. Human perception of our hearing perception is very good. We can very easily tell if something's real or fake with very little information, right? And we need our model to kind of be detail oriented, which is why we're going to make sure our model only looks at small chunks of audio, and these small chunks of audio need to convince the discriminators that they're real. The generators are convinced that these small chunks of audio are real. We're going to see all of that in just a minute here. So let's go ahead and start implementing. What we're going to need first is the MelDataset. So this is the actual dataset class that we're going to be using for everything. I'm going to go ahead and copy in all the boilerplate stuff that we're going to need, and we'll just quickly walk through it. So what we have is the path to manifest. This is the file from, let's see, let me pull it up, data, and then let's just look at the test metadata. The manifest is just a file, and the way I set it up is the path to an audio file. And then we have the transcript, which we don't really care about today. We just need the path. And we also have a duration, but we don't really care about that either for now, at least. Okay, so that's the path to manifest. We have our segment size. This is how many samples do we want to process in every single, basically how long should every sample be? So like I mentioned, it should be short. And our audio, the LJ speech audio by default, has a sampling rate of 22,050. This is higher than like LibreSpeech, which is 16,000, but that's fine. So we're going to use 22,050. 8192 is less than half. This is about 0.4 seconds worth of audio. And that's basically what we're going to be passing in. In 0.4 seconds, you can only utter like maybe 2 to 3 letters at the most at average human speaking rates. And so this is going to be a very detail-oriented model of how can this is how we pronounce a couple of letters. And our generator needs to be able to generate audio that is convincing the discriminator that that's what that audio sounds like, those couple of letters. We'll see all that in a second. We have our number of Mels and the hop size, window size. These are the standard setup for NFFT. These are standard setup for the short time Fourier transform and our Mel Spectrogram generation after that. We have a sampling rate. We have Fmin, Fmax, and an Fmax loss. We'll see why we have the Fmax loss a little bit later. We'll talk about that in more detail later. We have our max audio magnitude. This is just to match Tacotron. We have our min decibel, the max scaled ABS. We want to scale between -4 and 4. And then are we fine tuning? So if we're pre-training, we're just training on generated, things on spectrograms that we're generating right now. When we're fine-tuning, we'll generate some spectrograms from Tacotron and then use those instead, right? And then the path to the saved Mels, if that's what we're doing. We'll see all of that in a second. And the only things we need in this data set are going to be these. So we have these are all the common arguments that we're going to be using, nothing crazy. We're going to have 2 different Mel conversions, one with an Fmax and then one without an Fmax. And this is what I meant by we have Fmax and Fmax loss is none, and normal Fmax is 8,000. What this Fmax is basically indicating that when I create my Mel spectrogram, I want to make sure, or when I do short time Fourier transform, because that's where it's used, right? Let's see, where am I using Fmax? Yeah, so when I'm doing my conversion to Mel spectrograms, we can set ahead of time what is the maximum frequency representation we'd like to pass in. Which means any frequency, if I set this to 8,000, which is what it is by default, any frequency above 8,000 gets clipped out. Like we don't keep those frequencies. This is fine. The majority of human speech is between 0 and 8,000, which is why datasets like LibreSpeech is at 16,000 hertz. Because remember, half the sampling rate, the Nyquist rate, is basically the max frequency we can represent. So if our data is 16,000 hertz, 16,000 samples per second, we can theoretically represent up to 8,000 hertz. But if our sampling rate is 22,050, then theoretically the maximum frequency we can represent is 11,025, But that's, again, theoretical, and so we're just going to clip it to 8,000 because that covers it. And we'll see exactly why we do this in just a bit. And so we have one with the maximum and one with no maximum. And so we'll see. Def len, self. We have from our data set, our list of audio files. It's just the list of all the paths, right? All the paths to the audio files. So self is, we're just going to return len self.audio files. And then def get item self index. And so this will be pretty straightforward. So we're first going to do file name is going to be self.audio files index. So grab the paths to the audio, and then we'll do our audio, and sampling rate is going to be torch audio dot load. Just go ahead and just load our audio file name, and then our audio is going to be audio divided by torch dot max audio. The reason we're doing this is the same reason we do it for like MNIST images. Remember, MNIST or just normal images are between 0 and 255. We divide by 255, and that basically makes our data between 0 and 1, right? 0 and 1. So in the same way, our audio is between 0 and some max value, so we're just going to rescale it between 0 and 1. But we don't want it to be 0 and 1. We're going to make it 0 to 0.95 instead. The reason for this is because we're going to be doing like the log of this stuff and all that, and the log of 1 is 0, and if we divide by it, it can lead to an issue. So just to make it a little bit easy, we're just going to make sure the maximum value possible will be 0.95. So it'll be 0 to 0.95 instead, just for numerical precision reasons. And as a quick sanity check, right? If the sampling rate doesn't match, then we have a bit of a problem, right? So just make sure that the sampling rate of our audio matches this. We could have also like resampled the audio here, but everything is fine because this is the sampling rate for the data we're working on, so it shouldn't cause any issues. Now we're gonna have two branches, if not self.finetuning, else pass. So if we're not fine-tuning, that's no problem. What we're doing is just grabbing audio, grabbing a chunk of that audio, a shorter chunk of length 8192 samples, and then finding its Mel Spectrogram. So let's do that. So our if audio.shape1 greater than or equal to self.segment size. So this is assuming we have enough audio. If your audio samples are not longer than 0.4 seconds, then you probably have a different problem to deal with. These are all pretty reasonably long samples. So this should basically always happen, but it's just a sanity check. Shape1 minus self.segment size. And we're going to do audio. What we're going to do is just grab a random slice of the audio. So random.rand int 0 to max audio start. So just pick some random starting point from 0 to 8192 from the end. Because if you pick the last sample, then we just don't want to spill over. Right? We want to make sure we grab exactly 8192 samples. And so our audio is going to be audio. Ignore the channel dimension. And then we're going to be audio start to audio start plus self.segment size. If for some reason your audio is too short, we just have a sanity check, right? It's torch.nn.functional.pad. We're going to do audio, and we're going to pad 0 to self.segment size minus audio.shape1. And there we go. And we'll just add on some constant padding, or just add some 0 padding essentially. Just this really shouldn't matter, but just in case, there we go. Okay, now that we have that, we need to pad for Mel. Okay, so this is this small, where are we looking? Here we go, pad for Mel. Quick little method. Remember when we do our Mel spectrogram, we have a window size, which is typically the same as NFFT. So these two really should always be the same. They don't necessarily have to be, but it becomes more complicated if you don't. So there we go, some window size. And what we're going to do is move over by some hop size. So what this means is we have our window size is 1024 with the hop size of 256. So that means the very first sample, right, the first window is going to look at 0 to 1024, or 1023 technically. And the next one's going to look at 256 to, and it's going to go from 256 plus 1024 minus 1. The next one after that's going to go from 512 to 512 plus 1024 minus 1, ... Right? So basically it's like a sliding window, right? We have a window of 512 or a window of 1024, and it moves over by 256 samples every single time, right? And so just keeping that in mind, we need to make sure that everything is nice and evenly divisible, right? Evenly divisible, which means we need to make sure that we have enough padding on each side. And so if we add NFFT minus hop size divided by 2, so if we're doing, if NFFT is 1024 and our hop size is 256, so it'll be 1024 minus 256, divide by that 2, and then just add that extra padding on each side. So if we have, for example, let's say we have these samples right there, and we want a window size, window is 4, and our stride, or hop, right? Hop, we'll call it the same thing. Hop is 2. Then right now, what would happen is we'd have these 4 samples would produce an output, and then we'd move over by 2. These 4 samples would produce an output, and then, so 1, 2, 3, 4, and then these 4 samples would produce an output, and then these 4 samples would produce an output. And notice that we've run out, right? We don't have any more. So just to make sure we have enough samples so we have at least full completions on across the board, so we have basically the full window size always fits for all the samples, we're just going to add that padding on each side, right? So we'd basically add a 0, 0, or it's reflect padding, but it's fine. We're just add these as padding, and now it'll be these 4 samples, then these 4 samples, then these 4 samples, these 4 samples, these 4 samples, then these 4, right? So on and so forth. So basically we're just making sure there's enough space for everything to fit in. And we're doing reflect padding just so we don't add in additional frequency information, because if it was zeros, then we go from 0 stuff to actual data, and that would, there'd be a huge frequency jump there, and that wouldn't work out so well. So we're going to do reflect padding so no additional frequency information is added in. It's just little details. It also has one more purpose, but we'll see that in just a second. It's mostly just for convenience. Okay, so what we're going to do is our audio is going to be, let's see, it's going to be pad, or let's call this audio padded for Mel. It's going to be pad for Mel, and it's going to be audio self.nfft and self.hop size. And then our Mel spectrogram is going to be self.audio Mel conversion .audio to Mel, and we're going to pass in the audio padded for Mel, and do norm should always be true, right? We want it to be normalized. And our Mel loss is going to be exactly the same thing. Audio Mel conversion loss .audio to Mel, audio padded for Mel, do norm is true. The only difference is when we compute this Mel spectrogram is based on the transformation that has a maximum of 8,000. This loss, the second one is based on a Mel transformation that has no maximum. So this Mel has up to F max of 8,000. That's the highest the frequency information in this Mel spectrogram can be. This one, the second one, has no F max. It'll just be up to basically Nyquist, which by default will be 11,025. Right? We'll see why we do that a little bit later. It's mostly just to add additional, make the problem harder. We'll see that in a bit. It doesn't matter too much, but it's just detailed, and I'm trying to follow the HIFIGAN implementation as close as I can. And so each of these Mel spectrograms is going to return something that's basically shape of 1 by 80 by Mel time steps, right? Mel time steps, and we don't really need this extra 1 dimension at the beginning, so we're going to get rid of them. And we will return exactly this, the Mel.squeeze, get rid of that dimension, the audio, that slice of audio that we grabbed, and then the Mel loss, which is the same thing, just has no Fmax. And that's it. Now for the second part, and this is where it becomes kind of important, so let's just do a little bit of a quick aside here. I'm going to call this audio to Mel is audio Mel conversions, and I'm going to leave everything as a default for now. I'm going to create some random audio, ran head, and I know my audio is going to be in the shape of 8, and then let's do 8192. I know that's the shape that my audio is going to be in. When I actually do the Mel spectrogram projection on this, let's see what I get. Print A2M dot 2, or not dot 2, dot audio to Mel. Oh, cancel. Audio to Mel. And we're going to pass in the ran. And I'm going to open a new for audio. Again, okay, Python. Let's see this. Oh, I need to Okay, good. And I'm going to look at the shape of it. So this is my Mel Spectrogram. And notice it's 1 by 80 by 29. The reason it's 1 by 80 by 29 here, which seems like a weird number, is because I was not able to actually have full windows. So like I mentioned before, this pad to Mel method that we have right here, just adds some extra padding, reflect padding on each side, so we can have full Mel windows cover the entire sequence, right? There won't be like a part that just like can't cover the entire sequence. So we need to add that extra padding in. So let's add this pad for Mel in here real quick. So our rand is equal to pad for Mel rand. Let's print rand.shape, and let's look at the final output. The NFFT. FFT is 1024, and let's make it based A to M dot NFFT, and then our hop size is A to M dot hop size. Just make sure it's all the defaults. Now you'll see our 8192 samples here got upsampled, or not upsampled, we added some padding to 8960. But now we get an even 32 output Mel bins. This is super important to keep in mind, as it's going to actually define the rest of the architecture. What we have really is something that has 8192 samples, and it's being compressed down 8192 time steps, and it's being compressed down into something that has 32 time steps. Well, what is that? Let's print 8192 divided by 32. What does that give us? It should give us 256. And this is really important because remember, 256 is our hop size. So the hop size determines the downsampling factor essentially. So as we go from 8192 down to 32, we've downsampled by a factor of 256. To prove it, let's change this. Let's change our hop size to 512 instead. And let's print out the shape again. What you'll see now is we have 16. So our 8192 samples got sampled down, right, along the time dimension to 16 Mel time steps. This is 8192 audio time steps. This is 16 Mel time steps. This is a downsampling factor of 512, right? Because if 32 is 256, then down to 16 is 512. And 512 is the hop size. So this is really important. The reason we're doing this pad for Mel and then this quick audio to Mel transformation, it's because it's so we know exactly the scale factor. In the end, what this is going to end up looking like is we're going to have a batch, and let's kind of draw it down here. We're going to have a batch by 8192. This is going to be my audio, right? This will be the audio. My spectrogram is going to be batch by 80 bins by 32. And what I need to do is take batch by 80 by 32 and upsample it to batch by 1 by 8192. Well, that shouldn't really be a problem, right? Because 80 is a channel dimension, so 80 can go to 1, that's fine. And 32 needs to be upsampled by a factor of 256 to get to 8192. So this padding here is mostly for convenience, so our shapes work out nicely, and we get these nice like factors. Otherwise, we'd get that 29 if we don't do the pad for Mel. If we don't do this, right? Again, if we don't do this, then we're going to end up with this 29 here, which is basically because our window can't spill over on the extra steps, and we basically just end up not being able to cover the entire range with our windows, and so we're missing a couple. And so that's all that pad for Mel is doing. It's just convenience. Keeping that in mind, we're going to go ahead and implement this next part. So if we are fine-tuning, then what we're going to be doing is loading a Mel spectrogram. And like I mentioned, we're going to be producing these later. But we have right here, data, topogens Mel. We have a folder full of NumPy files. And these are Mel spectrograms that are already scaled and ready to go and have been produced by the Tacotron architecture. So that's our fine-tuning data. So we just need to load that. So I'm going to copy this little chunk and start to type it. Basically just grab the file name. It's based on the file name. And then just do .npy. And there we go. That will grab that spectrogram. Our Mel is going to be then torch.from NumPy, and then np.load path to Mel. Let's go ahead and load that. And here's the important part. Frames per Mel segment. How many audio frames does each Mel segment represent? So like we saw, if we had 1 by 8192, and that becomes 80 by 32, we have 32 Mel frame segments, each of which represent 256 time steps, because 32 times 256 is 8192. And this is why self.segment size, how many do we have? 8192, divided by self.hop size is how many frames we have per Mel segment. And that's basically it. That's the key idea, right? That's it. And so we can do if audio.shape1 is greater than or equal to self.segment size, which it should be, right, for most cases. Right, segment size being 8192 divided by 256, this gives me 32. This means I need 32 Mel frames, or this is basically saying how many Mel frames do I want, right? And that's based on the hop size. If the hop size is doubled, then the Mel frames could have, just like we saw, right? In this case, frames per Mel segment should be 32. Okay. And so now we can do Mel start. So we need to essentially index, we have the Mel spectrogram right here. So we need to grab a random slice of 32 frames, just like we did here. But here we slice the audio. Here we're slicing the Mel spectrogram first. We're going to do Mel start. It's going to be random.randint 0 to Mel.shape1 minus frames per Mel segment minus 1. So that's our indexing. So we can pick any starting point from here, no problem. And we can then do Mel is equal to Mel. Ignore the 80 dimension because it's 80 by time steps. So we need just Mel start to Mel start plus frames per Mel segment. So that's going to grab a slice of 32 time steps, Mel time steps from our Mel spectrogram, the ones that I already saved. And these are all 2 dimensions, so that they're all 80 by time steps essentially. Similarly, we need the corresponding audio that goes with this Mel spectrogram. That's fine. So we can do audio is equal to audio. And I know that I want to start from Mel start, and each of the Mel bins, right, each index in the Mel bins represents self.hop size worth of audio time steps, right? So this is going to be essentially if I want to start at Mel time step 2, that means I'm starting at audio time step 512. And that's basically the main idea, right? Because every Mel step represents Mel start times hop size, which is 256, time steps in the original audio. So we're just indexing back to the original audio shape. 2, Mel start plus frames per Mel segment, again, times self.hop size. So we're just indexing back to the original audio, and that just gives me my one-to-one transformation or relationship between the Mel spectrogram and the audio. Otherwise, if for some reason we don't have enough, which really shouldn't be the case, but if we don't have enough samples, then we need to pad our Mel spectrogram and the audio. Now, these Mel spectrograms are produced by Tacotron, and Tacotron was trained with a Fmax of 8,000, right, to produce spectrograms that have an Fmax of 8,000. But the actual audio may have more. I mean, most likely not, but it's possible, right? There could be higher frequencies than 8,000. Okay, no problem. All we need to do is for the loss, right, just like we had up here, we're going to have another Mel loss, which is another Mel spectrogram just with no Fmax. And that's relatively straightforward. We can just add that chunk in right here. Right, just grab, we have our audio right here, which we've sliced, right? So we have the audio, or, padded if we don't have enough. Go ahead and pad for Mel, compute the audio to Mel again with our melconv loss, which has no Fmax. So again, this one has no Fmax, and so it's set to 1125. This one, which I created, was trained with the Tacotron model that had Fmax of 8,000. So Tacotron only knows to generate up to 8,000. And that's basically it. We have Mel, audio, Mel loss, and we are done. We'll see why we have both of these a little bit later. Okay, good. So that is our Mel dataset. That's kind of the main dataset that we needed. Everything else should be relatively self-explanatory. Good. Let's now go on to the model. So the model is very straightforward for the most part, just some details that we need to keep in mind. So we're going to start with the generator. And just to kind of reference the paper as we are going, the generator is basically this. Generator upsamples the Mel spectrum up to k times to match the temporal resolution of raw waveforms. the MRF module as features from residual blocks from different kernel sizes and dilation rates. So what it looks like is basically this. We first have some Mel spectrogram. It's going to, or some representation, and it's going to go through a transform, a conv transform. And then it's going to be followed up by this MRF, which is going to be a bunch of different residual blocks with different kernel sizes and dilations. And each of those are going to be added on, and then we store them. This, I'll make a reference a little bit later, but this is kind of like the postnet of our Tacotron. So let me, oh, did I lose it? The idea is going to be kind of like this. Like in Tacotron, we basically produce some Mel spectrogram. That's what this linear projection does. It produces a Mel spectrogram. But then this Mel spectrogram also goes through a conv layer, and we add that in. So basically we have a Mel spectrogram. We pass the Mel spectrogram through another additional layer, and then we add that information in as like a residual connection. And this is supposed to essentially add in the information that was missing from earlier. This convolution is just post-process the Mel spectrogram, identifies what information is missing, and then adds that information in. So I'm going to kind of make an analogy here in a bit once we get there. I'm going to copy in this initial part, just our setup. We also have weight norm and spectral norm. I'll talk about that in just a second. This is specific to the paper. But we have this right here. We have our standard HIFIGAN config. Now let's understand some of this stuff. Remember that I said that our data is going to be batch by 80 by 32. That will be the spectrogram. And the corresponding audio is batch by 1 by 8192. So I need to upsample from 32 time steps to 8192 time steps. This is a 256 times upsampling. Well, here's our upsample rates, 8822. So 8 times 8, 64, 128, 256. This is our 256 upsampling. If this was different, if we did 16 here, then we need to set this up such that it's 512. We need to essentially match the temporal resolution. We have a upsample kernel sizes. So for every single one of these upsamples, we'll have some kernel. We have our initial channels. We'll see that in a second. And then we have some residual blocks. And these residual blocks, basically we're going to have a stack of residual blocks after every single upsample. That's what you see here. We have an upsample, that's a conv transpose, followed by a stack of these residual blocks. And we're going to see that. And each of these residual blocks is going to have a different kernel size, and they're going to have different dilation sizes. And we'll see why we do all that in just a minute. Let's go ahead and write a quick init weights. This is our standard, GAN initialization. So mean is 0.0, standard deviation 0.01, and if is instance, if the module is a nn.conv1d or nn.conv2d, then we're going to do with push.nograd m.weight.normal mean standard deviation, and we're done. There we go. Okay, so before we do anything, let's define this residual block, right? So this residual block basically has some kernel and some dilations, and we just do a bunch of them. So let's define them, and then hopefully it'll start to make sense. Class residual block and n.module. So a residual block does not change temporal or channel dimensions. It's basically just a processor. It doesn't change anything. It doesn't change the shape of the data, and we'll kind of see that in action. The definite self. We're going to have the input channels, whatever it may be. We're going to have a kernel size. It's going to be 3. And that's basically this kernel right here. And each one's going to be 3. The next one will be 7. The next one will be 11. And then the dilations. Dilation is going to be 135, which is this right here, 135. And this is going to be for each convolution in this module. We'll have a different dilation, and we'll see why in a bit. Okay, super dot init. So let's store self dot channels is channels, self dot kernel size is kernel size, self dot dilation is, and actually let's do self dot d1, self dot d2, self dot d3 is dilation. So those are our 3 dilations. And let's do our conv stack. So just to kind of start this off, a couple of small details that we just need to keep in mind. Weight normalization. So they use in their generator and discriminator kind of everywhere. They use something called weight normalization, which is right here. Subsequently, weight normalization is applied to MPD and everywhere else. But and over here, we see that we have weight normalization, and then we have our, what was it called? It was called spectral normalization. Weight normalization is applied except for the first subdiscriminator, which operates on raw audio. Instead, spectral normalization is applied as it stabilizes training, as is reported, right? So these are just implementation details that they've grabbed from other papers where GANs are pretty hard to train. There's always a bunch of instability, so a lot of work went into trying to stabilize them, and this paper just attempted to use all the tricks that previous papers for all sorts of applications used. So what weight normalization is, just to make it clear, weight normalization is essentially a decoupling method in PyTorch. What it does is it's a reparameterization that decouples the magnitude of a weight tensor from its direction. So both of these things are essentially learned independently. The weight, instead of just having a weight layer, what you're going to have is the magnitude of the weights as well as the direction of the weights. And it just, both of them are implemented separately. And so that one weight parameter becomes weight G and weight V for magnitude and direction. That's it. So it's just a trick. Here we go. And it helps with convergence, right? So it seems to help with convergence a little bit more. Reparameterization that decouples the length of those weight vectors from their direction. We improve the conditioning of the optimization problem and speed up convergence of stochastic gradient descent. How much does it matter? I don't know. I haven't actually tried training without it. And a lot of modern architectures don't really use these tricks, but that's there. And similarly, PyTorch spectral normalization, spelled that wrong. Here we go. It's another one, spectral norm. So this is one that's typically used. It stabilizes the training of discriminators in GAN setups, right? And what this does is essentially we take the weights and we divide it by some sigma W, and this sigma W is essentially just the max. It's, what do we call it? Yeah. So yeah, reducing the Lipschitz constants of the model is approximately performing a one iteration of the power method every time the weight is accessed. And this just gives you a spectral norm, right? Just spectral normalization. And it's simply like this, right? Basically dividing by the norm to whatever it may be. This is, again, these are small details that I'm not 100% sure how much they matter. I haven't tried training the model without it, but I don't know, the GAN paper initially found, right? So here you go, spectral normalization for GANs. They found that it helped with the stability of training. I'm not super aware of this being used in too many places today. So if it's there, let me know. I'm always interested to find better ways to train GANs. But that's it. So this is it. So it's just two little tricks that we will just incorporate into our model. So let's go ahead and do this. So we're going to do self.con stack. Okay, stack of three convolutions. Stack one is nn.module list. And this is going to take, I'll do the first one, but then I'll just copy paste the rest of it in because it's a lot of repetition. So we're going to do the weight norm of the nn.conv1d, and the in channels is channels, out channels is channels, kernel size is kernel size. Oh, am I missing a comma? Right there. Stride is 1, dilation is equal to self.d1, and then padding is same. So this is a dilated convolution. I'm missing a comma somewhere, I'm sure. Oh, right here. There you go. This is a dilated convolution. If you don't, they're also called archrous convolutions. Dilated convolution. Let me just pull up a quick figure here, just to remind you if you don't remember what this is. A dilated convolution is one where the filter weights are not touching each other. Normally they're consecutive, but you can see there's like a spacing between them. The purpose of a dilated convolution is to increase the receptive field. Basically, the filter, by spreading out the weights, it's looking at more at once, right? More of the image is looked at once, at least spaced out. And so dilated convolutions are especially popular for a lot of audio-related tasks because audio consecutive samples are densely packed. Like there's maybe not a ton of information from one sample to the next, but maybe by doing every other sample or every fifth sample, whatever the dilation factor is, you might have a better idea of the audio representations. More importantly, dilated convolutions also just increase, as you stack dilated convolutions, the final receptive field of those convolutions become much larger, much quicker, right? And especially in a task like audio where there's lots of samples, in our case there's 8192, we want to make sure that receptive field is nice and large so our model can see lots, so like future convolutions, deeper convolutions, can see more of the audio at once, essentially. So that's it. So these are dilated convolutions. They're very popular for all sorts of applications, but again, not a lot of stuff these days using it, at least for more modern architectures. And we also make sure the padding is the same. This way, when we pass our data in, remember data is going to be batch by channels, or batch by, channels, whatever the input channel is, by our 8192, we make sure that the convolution, the channels will stay the same, and the 8192 will not change as we're doing same padding, so nothing will change. And so that's it. This is a stack of these, 3 of them, right? So we have one of them, a second one with the different dilation, and a third one with a different dilation. So it's the same thing 3 times, each with weight norm, each with a different dilation factor based on 1, 3, 5. So dilation of 1 is default, no dilation, and dilation of 3 is spread out 3, dilation 5 spread out 5 increases the receptive field. In the same way, we're going to have another stack. So we're going to do the first self.con stack1.apply init weights. Just go ahead and initialize those weights with the normal distributions before. I will copy paste this as well. We have another stack of convolutions doing kind of the same thing, but there's no dilation here. It's just a normal convolution, non-dilated, with some kernel size of 3 or whatever it's set to, and padding the same. Again, this will not change the shape of the data. This is just a convolution. Now, what we're going to do is step forward, self, x, and here's the trick. So we're going to loop through them one at a time. We have 3 convolutions, we have 3 dilated convolutions and 3 normal convolutions, and we're just going to iterate between them. So we're going to do for proj1, proj2, the first one being dilation, second one not dilations, and zip self.con stack1, self.con stack2, loop through them. First, we remember this is a residual block, so we're going to store a residual, store that copy ahead of time, and we're going to do x as f dot leaky relu x, and negative slope is 0.1. Remember, leaky relu is really popular for GAN related things because relu has your vanishing gradient issue. Leaky relu does not, so we will be using leaky relu for the same reason here. X is proj1 x, so this is going to go ahead and analyze the signal, right? Analyze the signal, whatever data is coming in along the time dimension. It's going to analyze it with a dilated convolution. After that, x is again f dot leaky relu, just another one of these, no problem. And then x is equal to proj 2x. We're going to then analyze it with a non-dilated convolution. And that's basically it, right? The first convolution has a larger receptive field. It looks at more of it and aggregates that information. And then this one's going to look at that aggregation and essentially it expands that receptive field even more without dilation, because that's how receptive fields work, right? Every convolution is looking at the outputs of the previous convolution, and the previous convolution had, if it was looking at all these different things, that's spread out and aggregated into one position, then a grouping of those positions aggregate out even further. And so that's it. We're just basically looking at a dilated convolution output followed by a normal convolution. After that, we do x is equal to x plus residual, and then we return x. Now, the reason this is interesting and why I like this interpretation is that what we're doing, going back here, is basically each of these residual blocks are adding on to the output. It's adding on to that residual, as you can see here, right? We're just adding on every time. This adding notion is actually kind of important because in our Tacotron, remember, this postnet essentially is adding on information that's missing. Because remember, the very first thing we do is upsample. Technically, we could stop right there. Like, okay, we've upsampled the spectrogram, we're good to go. But this conv transpose may not capture all of the minor details that are necessary. So now what we're doing is we're following that up with some residual blocks that looks at the output of the conv transpose at some kernel size with multiple different dilations. So it has a different, each larger kernel size is larger, has larger receptive fields, and then the dilations only increase those receptive fields more. So at different levels of receptive fields, like looking at only 3 things with no dilation, 3 things with 3 dilation, 3 things with 5 dilation, And then again, we're looking at 7 things with no dilation, 7 things with 3 dilation, 7 things with 5 dilation, so on and so forth. By looking at them with different receptive fields, and adding the missing information in, that should help. That's the main idea behind this generator, where it's essentially just post-processing that initial upsample. And we repeat this upsample multiple times, of course, for every single chunk. So let's go ahead and write the generator now and see how it all comes together. Generator. nn.module. Here, I'll just copy in all of the boilerplate stuff just right there. So we're going to load it from our config file now. So this has all the information we need. And our effective upsample rate is, again, remember, it's going to be 8 times 8 times 2 times 2. So 256 in this case. So our first one's going to be input proj. This is going to take the original, this is the original audio coming in. It's going to be batched by 1 by, batched by 80 by 32. That's going to be the original spectrogram coming in. And we're going to upsample it this many times with these kernel sizes. So these are upsampling information. And then after each of those upsamples, we're going to follow it up with some residual blocks, right, with these dimensions. So the first one's going to be our input projection. That's going to take this and project it in a batch by, in our case, 512 by 32. This is the initial, right here, initial upsample channel. So it's going to be, again, weight norm and nn.conv1d doesn't change the shape of anything except for the channel dimension. So in channels, we config.num_mouse. Out channels is going to be config.upsample initial channel. And then our kernel size is going to be 7. Pretty standard to have a large kernel size like we do in ResNets as well, right at the beginning of the model to do some initial aggregation. And, oopsie daisy, stripes 1, and padding is same. So it's going to take our data and upsample it just like that. And now what we're going to do is our stack of generator blocks. And like I said, each generator block is going to have a upsample plus our multiple residual blocks that add on afterwards. So let's go ahead and do that. We're going to do self.generator blocks is nn.module list. We're going to do in channels is equal to config.upsample initial channel. That's 512 that we're starting with. And we're going to do for upsample rate kernel size in zip kernel size in zip config.upsample rates config.upsample kernel size. That's what I called it. Sizes. There we go. Okay. So for each one of these, we're going to do first our up block. So remember, each block will have another block in it. So we're going to do up block is again nn.module list. There we go. And out channels is equal to in channels divided by 2. So what we're going to do is every single block is going to upsample the time dimension. So right now we're at this, right? So after we do a single upsample block, it's going to become batch by 256. We're going to half the channel dimension, but upsample the time dimension by whatever the upsample rate is. In our case, it's 8, right? So it's the first one is 8, then 8, then 2, then 2. So it's going to be 8. So 8 times 32 is 256. And we're just going to repeat this every single time. So it's going to be, again, I think that's enough. So we have 256, then this will be 128, and this is going to be 256 times 8. What does that work out? 256, 512, 1024, 2048. And then this is going to be, again, 64 to 4096. And then we'll have one more. It's going to go to 32 to 8192, which is our end goal, right? That's our final time step. And we'll make this 1 later, right? There'll be a final convolution for that. So that's basically the setup. So let's do our up block dot append. Here I can do it. Remember, this is a upsampling. There's 2 ways to upsample, but they're using conv transpose, right? Transpose 1Ds. Don't need that. And this is going to take input channels, output channels, some kernel size, whatever the kernel size we set for this upsampling. We're going to have some stride. The stride will upsample by the factor that we state, as long as our padding is correct. So we need to make sure the padding is kernel size minus upsample rate divided by 2. And this will always ensure that we have exactly the upsample rate as our upsampling. So that'll make sure that our 32 will become 256 and not something like 255 or 257, because transpose convolutions are a little bit weird, right? They don't always give exactly the correct upsampling if you don't pad it correctly. So that's just the simple padding to make sure that we have enough padding on both sides of our signal so our transpose convolution can spill over the edge and get those extra windows in to make sure we've fit everything. And that's it. That is our up block. After the up block, very simply, we're going to follow it up like we see right after the transpose. We're going to follow it up with our stack of residual blocks. And this is going to be for residual kernel, residual dilation in zip. I don't even want to type this because it's a bunch of stuff. So paste it in. Right, residual kernel, residual dilation. So after every single upsample, we have 4 upsamples. Every upsample will be followed by 3 different residual blocks. And each residual block, we have 3 different residual blocks, each with a different kernel size. And each of those residual blocks will have 3 different dilated convolutions. And that's what you see here, right? So basically, we'll have one residual block, one of these blocks with a kernel size of 3, another one with a kernel size of 5, another one with a kernel size of 11, or 3, 7, and 11. There we go. So that's what it's going to be. So we have these residual blocks right here. And we can then do self.generator blocks.append up block. And this is basically one up block. It's a upsampling followed by a bunch of residual blocks. And then finally, our in channels is going to be equal to out channels, just to keep it going. Like I mentioned, this is going to go to batch by 32 by 8192 by the end of it, but we need this to become a 1, right? Because that's what our audio is. It's one channel audio. So we have a final convolution, right? Self.output proj is, again, waveform nn.conv1b. In channels is going to be the final out channels. Out channels is just going to be 1. Because we're working on, mono audio. If you're working on like binary audio, then you have to change it to that. Kernel size will be 7. Stride is equal to 1. And padding is equal to same. That's it. And this will not change anything about the shape of the tensor. Just map the final 30 channels to just one channel. And we are good to go. And we can go ahead and initialize all the weights of these as well, just so they're good to go, right? Standard weight initialization. So let's see how this all comes together. And this will kind of go back to that, that note that I made earlier about essentially the residual blocks post-processing our data, our upsampling. So it's going to be def forward self x is going to be self.input proj. That's going to go ahead and map to the 512 channels from the 80 input channels. And for I in range, self.num upsamples. So for every single upsample, our block is going to be self.generator blocks. So that's the block we're going to be working on. And the first thing in that, so remember, this is also a module list. This block is a list of a bunch of stuff. Our upsample is going to be the first thing, and then the residuals is everything else. So we block 0 and block 1 to the end. That's everything else. And we're going to start with first, x is f.leaky relu x 0.1, and x is upsample x. And here's the key idea. What we want to do is pass in this upsample data into every single one of these blocks. So basically the output of this conv transpose is going to go to each of these res blocks independently, and we're going to aggregate that information together. So what that looks like is basically this. We're going to do x is equal to residual x for residual in residuals. So what I've done is, remember, this is a stack of a bunch of residual blocks, right? That's what this is. This is basically a list of residual blocks. And I'm going to loop through each one of them and pass in the upsample data. This is essentially one of the residual blocks. We'll have 3 of them, but it'll be one of them that takes in that input and then passes it through all our convolutions and post-processes them, right? We're basically adding in missing information. That's what these residuals are trying to learn. It's looking at our data, the input, with different lenses, right? Different kernel sizes for every residual block. And then we're adding in that information, essentially post-processing it, right? And then what we do is we repeat that for every single residual block, because the first one's going to look at it. So if we go back up here, the first residual block is going to look at it with a kernel size of 3. Another one's going to look at it with a kernel size of 7. Another one's going to look at it with a kernel size of 11. These are all going to have different receptive fields, so they're all going to see the tensor in different ways, right? They're going to learn different things about the tensor because they all have different time dependencies, right? How much time they can all see at once. The one that's 3 is going to be more focused on minute details, small things that it can only look at with its small receptive field. Things with an 11 kernel size has a much larger receptive field. It'll be able to see more of the data at once, and this will see the data in a different way, right? It'll have a different quote-unquote view of the data and what's missing from it. And each one of them in these residual blocks will be looking right here. We'll be looking at that data, right? These are those dilated convolutions followed by a normal convolution. They'll each look at them and then add in what it thinks is missing, right? That's the post-processing. And that's kind of the interpretation I have of this. And so each residual block will post-process this X differently. And what we're going to do then is average that up. So we're going to stack it, torch.stack, and then .mean dim equals 0. And that's it. So each residual block will post-process this input X differently, and we're going to average up all those post-processings just so we get the overall representation of what all the residual blocks thinks this thing should be. And that's basically it. X is then equal to f dot leaky relu X 0.1. We then have X is self dot output proj X, and then X is torch dot tanh X return X. And the reason we're doing tanh here is to scale the data between -1 and 1. Our actual targets are going to be between -4 and 4, but we'll handle that later. For now, this is fine. And that's it, right? That is our generated data. Nothing too crazy. Okay, now that we have that, it's time for our discriminators. So like I mentioned, there's 2 discriminators. We have the multi-period discriminator, and then we have our multi-scale discriminator. And the multi-scale discriminator is basically from the MelGAN architecture, right? So nothing too new here, and this will be pretty easy to implement. The multi-period is the more interesting one. Let's just kind of detangle this figure, right? Let's do it ourselves. So let's just start the implementation, and then I'll draw it up. Periodic discriminator. I'm going to write this out right here. There we go. So this is a discriminator that's going to look at the periodicity of the audio. So let's first look at what period is. So if we look at pitch, there's this great little website here called Auditory Neuroscience, if you want to look at it, but I found this. It says that pitch is determined in most cases by the periodicity of the sound waveform, right? So there's a bunch of stuff in audio that we can measure, one of them being like the fundamental frequency. The fundamental frequency, F0 or F1, is the lowest typical sound frequency of a periodic waveform or vibrating object. Everything has a fundamental frequency. Your voice has a fundamental frequency. It's F0 score, and you can actually compute it. There are ways to compute your pitch for your own voice. But that's exactly what it is. It's basically a periodic signal that exists as one of the frequency portions of your overall voice, right? So it defines the root pitch, while higher harmonics overtones determine the timbre or tonal quality. There's all sorts of reasons for this. But the important part is that it is periodic. It is a periodic waveform. And periodicity kind of represents a lot of stuff. Like this is periodic audio. You can see that this kind of pattern is repeating over and over again. And periodicity kind of happens everywhere. Even in random looking waveforms, there's internal substructures, frequencies that are periodic, or even, mixtures of frequencies. So just to kind of read their paper just a little bit, let's maybe go right here. I think they had a good one right here. Okay, as speech audio consists of sinusoidal signals with various periods, we demonstrate that modeling periodic patterns of an audio is crucial for enhancing sample quality. This was the main novelty of the HIFIGAN paper. So let's just see exactly how this works out in practice, right? Because, I X out of the, that's fine, I can open it again. Let's say we have some data like this. This is going to be x0, x1, x2, x3, x4, x5, x6, x7, actually x7 is good. And let's say we pick a period, right? We had to pick some period, is 2. Now, I just mentioned that your voice has a fundamental frequency. There is a specific period that your fundamental frequency repeats at. This is computable, but for any arbitrary audio, I don't really know what the periodicity is. And so when we don't know, we're just going to try a bunch of them. And that's why it's going to be called multi-periodic discriminator. Each discriminator is going to look at your audio with a different periodicity. And so let's just look at how one of them work, and then it'll kind of make sense. So let's pretend we pick a period of 2. This means what we're saying is that every 2 samples, in this case, it's very limited, but every 2 samples, we have some type of repeated substructures. So what that'll look like is like this. We'll have X, here, let's maybe copy this in. There we go, and we're going to repeat this 4 times. So the first one's going to be X0, X1. The next ones are going to be X2, X3, like that. Then X4, X5, like that. And then X6, X7. So what we've done is we've taken this data, which is batch by 1 by 8, and we've converted it to batch by 1. There's still a channel dimension that we don't care about, but the 8 gets split up into 4 by 2, where basically it's going to be batch by 1 by num samples divided by period by period. That's the actual shape, right? That's basically what it works out as. And what I'm saying is that in these periods of 2, so in this period of 2, this chunk of 2, this chunk of 2, this chunk of 2, there is some repeated representation. Something repeats in these chunks. And so if we compare, what this discriminator is going to do is it's going to look at one of these sets from a true data, right? From true data, our ground truth, essentially. And then we're going to have another set that's generated, right? Generated. This is what this generator we just wrote will produce. If we see that there's some discrepancies in the substructures, right, of what we see in these repetitions, then the discriminator will pick up on that. So what the discriminator has to do is check across this column here, right? Basically here, is there any discrepancies compared to this here? Across this column here, is there any discrepancies compared to here? So on and so forth. Because we would assume that if the audio was truly periodic in samples of 2, x0 should technically be equal to x2, equal to x4, equal to x6, and x1 should equal to x3, x5, x7. Because it's repeated, right? We're quote unquote assuming that we're repeating, these samples repeat every 2 samples, because that's what it means to be periodic. And so, of course, that won't exactly work out to be true because I don't know what the periodicity is. It could be 2 samples, it could be 7 samples, it could be 25 samples. I have no idea. And that's why we're just going to be testing it at different periods, because at least one of them should contain some type of periodic information, because there has to be some kind of substructure to audio, because every voice has pitch. It has fundamental frequency. So we just don't know exactly what they are. And so what this is, well, think about it. This is batched by channels by some height by width. This is basically an image, right? I mean, it's an image that's 4 by 2. And so what we want is a convolution to process the columns of this. It needs to look at this column and see, is there any repeated structures? And then it's going to look at this column. Is there any repeated structures? And the discriminator is going to identify some repeated structures of the true data. Then it's going to look at the generated data and say, do I see the same repeated structures here and here? No? Then it must be generated. Yes? Oh, this must be real. And that's basically what the periodicity, the periodic discriminator is doing, just to make it kind of clear with a better image from their end. Did I close it by accident? Oh, I might have closed it by accident. Let me just pull it up one more time. HIFIGAN paper. Here we go. Here we go. So the multi-period discriminator, we have some time steps. Because it's periodic, it's going to essentially just sample, right? In this way, this is transpose because we go batch by channels by height by width, but they drew it width by height, which is a little bit confusing, but that's fine. And they draw it this way. And then essentially we have a convolution across the height dimension, right? Across the time steps, because we would assume that every single one of these should be identical because it's periodic, right? That's the assumption of periodicity. So scrolling down right, or scrolling up right here, we can see MPD is a mixture of subdiscriminators, each of which only accepts equally spaced samples of an input audio. The space is given as a period of P. The subdiscriminators are designed to capture different implicit structures from each other by looking at different parts of an input audio. We set the periods to 2, 3, 5, 7, and 11. So these are the periodicities that they pick to avoid overlap as much as possible. As shown in figure 2b, we first reshape the audio, then apply a 2D convolution. In each convolutional layer, we restrict the kernel size to the width axis to be 1. So basically, we can only process, let's look at it kind of how the data will actually look. Every kernel only processes a column. It can't go across the rows. It just looks at one column at a time, what's going on. So every column is processed individually. Or that's basically what the convolution does. And then we have some convolutions with the leaky ReLU. We have some weight normalization, that sort of stuff. And this little chunk here is basically the novelty. This chunk here is the novelty of this paper, right? That's the main novelty of this paper. So let's go ahead, and hopefully this made sense so we can start to piece it all together. So what we're going to do is very simply, already did that. So we're going to do self.conv blocks is going to be nn.module list. And I'll type one of them out, but then after that, it's just it's repetition, right? So we don't need to type all of them out. It's going to be nn.conv2d. And so in channels is 1, out channels is 32. Kernel size, so of course it's going to be one input channel because the audio starts as batch by one channel by 8, right? But it'll actually be this, batch by 1 by 4 by 2, because we'll already have reshaped it before we pass it in. The kernel size is going to be based on whatever kernel size we identified up here, so kernel size. We're going to have a stride, and here's where it gets a little bit more important. The stride, we want the stride along the column dimension, so the first dimension, to be whatever we set it to. So this is the stride. But we want the stride along the this dimension to be 1, right? We want to basically have it move over one at a time, one column at a time, but the stride in the column dimension can be whatever it wants to be. And so that's all it is. And then our padding is equal to 2, 0. The reason it's 2, 0 is because our kernel size is 5 by default. So technically this should be kernel size divided by 2, but I'll just hard code it just to keep it simple right now. The padding is 2, 0 because I want to make sure my convolution doesn't change the shape of the data. Whatever this is, it should stay the same. So because I have a stride of 1 here, I know that this shape won't change at all, right? This is not going to change on the second dimension. But because I have a stride of 3 in the height dimension, this one could change. So we need to add padding before and after, essentially, and that's a padding of 2. By adding a padding of 2 with a kernel size of 5, we ensure that the final shape is always the same. And so that's it. We just have this extra little bit of striding and padding logic that we need to include, but other than that, it's basically the same thing, and we just have a bunch of them, right? You stack them all on top of each other. We're going to go from 1 to 32, kernel size 1, kernel size, and then 1, stride 1, 2, 0. And I just repeat it over and over again. 32 to 128, 128 to 512, 512 to 1024. In the last one, all that changes is not much. This is basically going to have a stride of 1 and 1, right, by default. But we'll just have a stride of 1 here. This is just based on their implementation, right? So I'm just trying to follow it there. So we have our quick computation going to 1024 channels. Again, processing mostly along the height dimension with padding just so it doesn't change. And everything is good to go, right? Nothing will then change. Okay, and then we have self.output proj. The final projection is going to be, again, weight norm, nn.conv2d, and in channels is going to be 1024 because that's what this final thing outputted. Out channels is going to be 1. Our kernel size is going to be 3, 1. Our stride is 1, and padding is 1, 0. And this, again, just makes sure that the These kernel size and strides and paddings were selected, so the shape of the data, batch by 1 by 4 by 2 or whatever it may be, doesn't change. Just the channels go from 1024 back down to 1, and that's it. So the forward pass is pretty straightforward. Def forward self x. Feature maps, we're going to store. This discriminator will actually have two purposes. The first one is we want the final output of all of these layers, but we also want to store intermediate outputs of each of these layers, and we'll see why later, right? But for now, just keep that in mind. Data coming in will be batch size by channels by sequence length is equal to x.shape. And what we want to do is x equals x.reshape batch size by channels, and then we're going to do sequence length divided by self.period, like I showed earlier, and then self.period. So that's going to go ahead and do everything. The problem is this: what if the sequence length is not divisible by self.period? That would be kind of annoying, and not something we can really avoid. So we just need to do one quick thing of padding. We need to do if sequence length percent or modulo self.period does not equal to 0, then we have to just pad it. We have to do npad is equal to self.period minus whatever that difference was, sequence length percent self.period. Right, so we're going to pad. X is f.pad x. We're just going to add npad to the end of it. We're going to do reflect padding. This way, we are not introducing new frequency informations by just like doing 0 padding. And then our sequence length, we're just going to become npad, right? Basically, you've added on npad tokens or positions, time steps, to our original data. This just makes sure that the data is always the sequence length is always divisible by period, just in case we need to do that. And now we're going to do for conv in self.conv block. X is conv x. X is f.leaky relu x 0.1. And then feature maps, like I mentioned, .append x. And that basically, what we want to do essentially is just store from every single convolution their intermediate representation. We'll see the use for that later. For now, we don't really care. X is then self.output proj x. Store that. And feature maps.append the final representation. And then x is equal to torch.flatten 1 x 1 negative 1. And so remember, our data, the final outputs can be essentially batch by 1 by basically these two dimensions. We'll put that right there. And we just want to flatten all this. So we can make this, we don't really care about the 1 dimension because it's just a dummy. So 1. And then we're just going to put all this back together. So it'll be, it would be that times self.period, which, they cancel. And so really we're just left with batch by sequence length. That's the reshape that we just did. So it's just batch size by sequence length is the final output. We're just flattening it out. And now that we've done that, we can return x and the feature maps. And that's it. That is our periodic discriminator. Nothing crazy. It's just, again, all it's doing is taking the data, cutting it up into periods of whatever size we say, and then look along the periods to see, is there any repeated representations? And if the true data, which it should have some repeated representations, as true audio has fundamental frequencies and pitch information and things like that, then the generated one should mimic that. And the discriminator is going to force our generator to make sure it's creating representations that actually contain that type of information. Or if the generator is synthetically producing some type of incorrect periodicity here, some type of some type of random frequency is being generated, then the discriminator is going to say, hey, I'm seeing some repeated periodic frequencies here that the true one doesn't have. So again, it needs to match these two. And that's exactly what this periodic discriminator does. Of course, we don't know what the period is for audio, right? It's different for every single person, every single voice. And that's why we're going to have multiple of them. So multi-period discriminator. And then .module. And this is pretty straightforward. Def init self config super dot init. And we'll do self.config is config, and then self.discriminators is going to be, and then .module list periodic discriminator p4 p in config.mpd periods, right? So we've already defined in our config the number of periods, or the period size, for each of the discriminators. So in this case, we have 5 of them with these periodicities. There we go. And of course, not all of them will be useful, right? If there's nothing in your data, in your audio, that has a periodicity of 2, then, well, this doesn't really, that one won't really be used, but at least some of them should be used, right? There should be some type of periodicity in your data. So hopefully at least one of these discriminators will capture that. If you actually know something about your data, you can select a period that might be more ideal, but this is what we're going with to be close to the paper. Self, we're going to pass in the real images and the generated images. We'll have real outs. I'll just paste this in. It's very simple. We'll have a real outputs, generated outputs, and then the real feature maps and generated feature maps. And for every single discriminator, we're going to go ahead and inference them. Into the discriminator, we pass in the real data. To the discriminator, we pass in the generated data, append them, and store them. So each of these outputs actually are going to be a list of lists. So inside, right? So inside this, each item, each list will go with one of the discriminators, and that internal list will contain the representations from the different convolution blocks from that specific discriminator. Right, so that's it. So it's going to be a list of lists, and that'll be important later. Okay, now we have our scale discriminator. This one is quite a bit simpler. The scale discriminator basically takes data at the original scale, average pools them, and then applies it a convolution, right? Basically, that's it. So the scale discriminator just looks at the original data and then pulls it and then looks at it at the new scale, which is half the sequence length. And then it pulls it again, and then again, half the sequence length. So it's multiple scales along the time dimension. And this is exactly what MelGAN did, right? This does, except disjoint samples, we add MSD to consecutively evaluate the audio sequence. The architecture of MSD is drawn from the MelGAN architecture. It's a mixture of 3 subdiscriminators operating on different input scales: the raw audio, a 2 times pooled audio, and a 4 times pooled audio. Each of the subdiscriminators is a stack of starting group convolutions, yada, 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 right? So that's it. The main reason for this is the multi-period discriminator doesn't really look at the data in sequence. Remember, from up here, we don't do any kind of sequence processing. The convolutions go along the columns, so they're processing disjoint. So the first convolution is processing x0, then x2, then x4, then x6. The next one processing x, and we shift over by 1, then x1, x3, x5, x7. So they're processing disjoint samples, which is why you see this color coordination here, right? Orange, 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 because that's what the convolution is going to process, disjoint samples. And of course, disjoint samples are important in the case that we want to extract periodic information, but also contiguous samples, right? Or, samples next to each other, analyzing those are just as important. And that's exactly what this convolution does, the scale discriminator. Scale discriminator is very simple. I can actually just paste this, this first part in because nothing has changed. It's just a bunch of convolutions, kind of the same as before, but with 2 differences. The first one is we can use either weight norm, or in the paper they found that the paper they cited found that using spectral normalization on the original input and then weight normalization on all the other pooled inputs seemed to help with training stability. So there's that. We'll see that in a second. And then the convolution is essentially just a bunch of 1D convolutions, because again, now we're processing 1D signals. We're no longer doing this reshape to like an image shape kind of thing, so they're 1D signals. And we can see we have relatively large kernel sizes. Large kernel sizes, we're using grouped convolutions just to make sure that the grouped convolutions make sure that we're doing different kinds of processing for different chunks of the channel dimensions. And the large kernel sizes make sure that we're looking at large swaths of the audio, right? Large amounts of the audio's temporal dimension with each of these convolutions, because we want this to process it in the temporal dimension. And at the end, we're going to do the same thing. This does not change the shape of the data in any way. We're going to output one channel, and our forward method will look basically identical to what we had before, right? So we're first going to do a convolution, Lihi-Relu, store those intermediate feature maps from each of these convolutions for later, and then give our final output, and we're done. So the multi-scale discriminator, class multi-scale discriminator, and then .module, definite self-config, super.emit, we're going to have self.config is our config, and then self dot, and I'll just paste these in. They said that there's 3 discriminators. One that happens on the original audio sequence, and this one will have spectral norm, and then 2 more that will happen on those downsamples. And to do the downsamples, we're going to use an average pool, and basically they decide to use a kernel size of 4, strider 2, padding of 2, and this just makes sure that we downsample the entire signal by a factor of 2. And so what our forward method will look like is kind of the same thing as before. For itself, we're going to have real, gen, and we'll have all of these, right? Just store those intermediate outputs. We're going to do for I, discriminator, enumerate self dot discriminator. So for each discriminator, we're going to do if I does not equal to 0. Because for the first sample, we don't do this. But for every one after that, the first one goes on the original audio. Every discriminator after that goes on downsampled versions of the audio. If it's not the first one, then real is going to be self.mean pools I minus 1 real. And similarly, we're going to do gen is self.mean pools I minus 1 gen. Just go ahead and downsample the real audio and the generated audio. And then everything after that is kind of identical as what we had before. Right? Go ahead and compute our real out and those feature maps from those intermediate convolutions, the generated out, the intermediate operations for the generated stuff from our discriminator. Go ahead and store all of them and return them. And again, this is going to be a list of lists, right? Where the initial list index is how many discriminators we have, and then each of those internal lists will have 1 output per convolution, right? Per convolution. And now that we have all of that, our HIFIGAN architecture is very straightforward. HIFIGAN is just a generator, 2 of the discriminators, and I wrote some helper methods to get the generator parameters, self.generator parameters, and then get discriminator parameters, which is both the MPD and the MSD parameters together. And that's it. That is our model. It's not complicated, just a little bit of interesting shape manipulation, but it's all fun. Let's go ahead and now implement our losses, right? So losses, and we should be good to go to then to write the training loop. So import torch. We're going to have 3 losses. Feature loss. Let's do this first, feature loss. Let's see if we can find in the paper real quick. Feature matching loss. Basically, the feature matching loss is a learned similarity metric between the difference in features of the discriminator between the ground truth sample and a generated sample. And it was successfully adopted to speech synthesis as an additional loss to train the generator. And basically, every intermediate feature of the discriminator is extracted, and the L1 distance between a ground truth sample and a conditionally generated sample in each feature space is calculated. This sounds super fancy, but all that's happening is basically this. We've stored, like what we have here, we'll be doing it both for the multi-scale and for the multi-period, but let's just look at multi-scale for now. We have the feature maps from all the convolutions on the real images, or real audio, I might have kept saying images, real audio. And then we have the generated, we had the feature maps of the generated audio. And we want to make sure that those intermediate representations from these different convolutions, like whatever this convolution says about the real image, should be close to real audio, should be close to what it says about the generated audio. I might have said image a bunch, way more than I thought. Sorry, audio, I mean to say audio. So basically, this convolution, if it extracts some information about the real audio, whatever features it extracts, it should be the same or very similar to that of the generated audio. So the generator's goal is to make sure that it's matching the features that the discriminator extracts on those inputs. And that's basically it. So the feature matching loss is pretty straightforward. We already computed and stored all of those features right here, the real features and the generated features. And we have them, remember this is a list of lists, the first set of lists being all the discriminators, this internal list being the outputs of those different convolutions. So we just need to iterate through all of them. We're going to do loss is 0, and we're going to do for feature real, features gen in zip, feature map real, feature map gen. And then we're going to do for feature real, for feature gen, or feature real, feature gen in zip, features real, features gen. So This loop is looping through the different discriminators. Each discriminator will have its own internal list of the different convolution outputs. So these are those individual convolution outputs. And we want to make sure that the generator generated a audio such that the discriminator's features are close to the real ones, right? That's basically the main idea. So we're going to be loss plus equals torch.mean, torch.abs, feature real minus feature gen. It's simple. It's just an L1 loss. It's just simple L1 loss, and we can return loss times lambda feature. They pick a lambda of 2 for its weighting. It's somewhere in the so whatever here we go. Lambda feature loss is 2, lambda mel is 45. So we'll see that in a second. So lambda feature 2. We have a discriminator loss, disk real outputs, disk generated outputs. So this is basically this output right here. So the real outs and gen outs, or more specifically, let's just look at a single scale discriminator or period. We had this x, right? And the x is the final output of the discriminator. And so we just want to make sure that our final output predicts 1 if it's real or 0 if it's not real. Now, here's a small trick. They inherit, in this paper, they inherit the LS-GAN loss. So this is the right here, GAN loss. They use the LS-GAN. So this is the least squares GAN. So LS. Oh, that's not helpful. Let me just find it again. Right here. There we go. LS-GAN loss. Basically, in the normal GAN loss, what we do is we do binary cross entropy, right? Basically, the discriminator should predict the real images as 0 and generated images as 1, or vice versa, however you want to do it. Instead of doing that, instead of doing binary cross entropy, we will use mean squared error. So let's kind of see how this works out. We're going to do loss is 0, and we're going to do for dr, dg, and zip disk. Remember, we're going to have one of these from each discriminator. Disk real output, disk generated outputs. We'll do r loss is equal to torch dot mean. We want our model to predict that real things are 1, right? Basically, that's we want real to be 1 and fake to be 0. So we're going to say that we're going to do 1 minus dr squared, right? We want our model to predict that this is real. So just take dr minus 1, square it up, and average it all together. And that's it. And we wanted to predict that fake things are 0. So we're going to do torch.mean, and it will be technically 0 minus dg squared, but the 0 doesn't really matter here then, so we can just do dg squared. And our loss plus equals r loss plus g loss, and then we can return loss. And that's it, right? So basically, instead of doing a hard target of 1 and 0 like we do in binary cross entropy, mean squared error kind of makes it like a soft target. Like we want dr to increase towards 1, we want dg to kind of decrease towards 0. We could have also used any other loss, Wasserstein loss, hinge loss, any other GAN loss, but this one is the one they used because LS loss proved to have less vanishing gradient issues during training, right? Okay, good. So that is our discriminator loss. One thing, this is actually a little bit like the patch GAN, because remember, the dr is going to be the shape of batch by sequence length, right? Batch by sequence length. Like each of these DRs are going to be batch by length, essentially. So we're predicting at every single time step, is it real or is it fake? So the model needs to not predict is the whole signal real or fake, but rather is every time step real or fake? And all those time steps need to go up to 1 or to 0 if it's real or fake. So it's, it's a little bit like the patch GAN loss. Similarly, def generator, or not similarly, but the backwards of this is going to be disk outputs. So the generator is, the goal of the generator is to predict the discriminator. So we're going to provide the discriminator generated images, but what does the generator have to do? It has to do opposite of what the discriminator was doing. So in the discriminator wants the generator loss to go to 0, right? We want dg to be close to 0. So that means the generator wants the discriminator loss for the generated image to go to 1. It has to be exactly backwards. We're going to do for dg in disk output. L is torch.mean. 1 minus dg squared. Loss plus equals L. Return loss. So it's exactly the same thing, except it's backwards, right? In here, in the discriminator, we wanted our real images to equal to 1. But the generator wants to update in such a direction such that the discriminator thinks that the generated images is equal to 1. So that's why the generator loss is basically just backwards of the discriminator loss. And that's the standard way. And you can see that's exactly what they do right here, right? We want the generated images to be predicted as 1, so we do the mean squared between them. And there we go. That's essentially our 3 main loss functions. So we'll have the GAN loss, we have the Mel Spectrogram loss, which we haven't done just yet. We have a feature matching loss, which we've done, and then we do the aggregation between all of them. The Mel Spectrogram loss is also just as important, right? So we will see that in just a second. So let's go ahead and start implementing that. We're finally on the training loop, right? Training loop. I'm going to go ahead and copy in all the boilerplate code in the training loop. So this is all the stuff that we've imported, we've implemented, or had from before. We're going to be using standard Hugging Face accelerate to train this model for simplicity. So I'm going to copy all of this stuff and we'll just walk through it because there's nothing of interest except just boilerplate. So there's a lot of little things here, but let's just walk through it real quick. So this again defines our config. We have our training config, how many epochs, train for 3100 epochs, how often do you want to print, batch size, beta. The reason we're using beta 1 of 0.8 is because in GANs, we typically reduce the beta values a little bit as it helps the model be slightly more dynamic, right? Dynamic in updating. In Atom, the optimizer we're using, beta will essentially smooth out the gradients too much. And this is typically seen in GAN that too much smoothing doesn't help with GAN training. So reducing the smoothing by reducing our betas helps. And there you go. We then have if we're fine tuning, that's our config. We'll see that later on. We have our model config. This just defines the structure of the model. And then we have our dataset config, all the defaults that we've already seen. What we're doing here is we are initializing our accelerator like always. So we can train on multiple GPUs. We have our HIFIGAN model right here. So we loaded that. We have 2 optimizers, one for the model, one for the discriminators. We have 2 schedulers. They use exponential learning rate in their model. So we're going to do the same thing. Again, one for the generator, one for the discriminator. We have that MelDataset we implemented, one for the training dataset, one for the validation dataset. And we go ahead and load our data loaders for exactly those. So we're good to go there. We have our audio Mel conversion. We're going to need this in a bit. You'll see exactly why. So don't worry about that just yet, but we need the ability to convert audio to Mel and stuff like that. So that's the audio Mel conversion method that we already had in our dataset, what we've looked at, this one. And then, of course, we need to prepare everything. This will prepare everything for DTP, distributed training. So we're good to go there. We can load pre-train weights. So if we are fine-tuning, so let's kind of go back here. During pre-training, what we're doing is we're taking audio and converting to Mel spectrograms and then reversing the process. This model has to essentially reverse that process. But like I mentioned, there's going to be some potential domain gap between true Mel spectrograms that we produce from audio versus generated Mel spectrograms from a model like Tacotron. And so because of that domain gap, fine-tuning is just the second stage of we have a model that can take spectrograms and convert them to audio pretty well. That's what HIFIGAN will do. But there's a slight difference between the generated Mel spectrograms versus true Mel spectrograms. And so let's just fine-tune on generated to do the same thing. Take generated Mel spectrograms, produce the waveforms. And that's exactly what we did in our dataset. In the Mel dataset, we had the second part of loading Mel spectrograms. We'll take a look at that in a bit. So we can, if we're doing that, then we need to load the pre-trained HIFIGAN model that we've made, no problem. Otherwise, if we are, if we're loading from a checkpoint, then load the checkpoint, standard Hugging Face, or accelerate method of just loading checkpoints, get what step we're currently on, resuming from there. Otherwise, we're just starting at the beginning and we're done. So for epoch in range, completed steps, completed epochs, training epochs. So for every epoch, we're going to go ahead and print out this. And here's where it gets interesting. So we're going to do for Mel, audio, Mel target, which is that Mel loss in train loader. reminding you again that the first Mel has an F max of 8,000, like we saw, right? So this one right here has a F max of 8,000, maximum frequency of 8,000. The Mel target has a maximum frequency of 11,025, or just no max, right? So whatever the audio has. We'll see exactly why we do that in just a second. For in train loader, we're going to do Mel is equal to Mel.to accelerator.device. And we're going to repeat this for the other ones. So Mel, and we're going to do it for the audio and for the target. Make sure everything's on the correct GPU. And then our gen audio is going to be accelerator.unwrap model. This is a little bit annoying, but it's a accelerate specific thing. When we do accelerator.prepare, this basically wraps our model and discriminator, everything, so our HIFIGAN model in the DDP wrapper. To actually access internal methods of that model, we just need to do this quick unwrap model. It doesn't really do anything. It just lets us access those internal methods. That's all. Dot generator model Mel. Sorry, pass in the Mel Spectrogram. So what we do is we pass in Mel specs that have max frequency of 8,000. Right? That's what we did here, and it produces some audio. And what we're going to do now is we're going to compute the Mel spec for generated audio. And this is where it becomes crucial. And this is the cycle consistency we want. If we have a Mel spectrogram and we create some audio, but then we take the audio and convert it back to a Mel spectrogram, well, the initial Mel spectrogram and the final Mel spectrogram based on the generated audio should be the same. Right? If I take Mel spectrogram, create an audio, take the audio, make it back Mel spectrogram, the input Mel spectrogram and the final Mel spectrogram should be exactly the same. Ideally, right? That would mean it's a good generation. And so to do that, we just need to take this generated audio and convert it back. And this is why we're going to first do gen audio padded is going to be pad for Mel. It's going to be gen audio, nFFT is args.nFFT, and hop size is args.hop size. Hop size. We basically want to go through the same process that we did earlier. In our data set, we have audio, and to convert that audio, in our case it's generated audio, but audio we first pad for Mel, and then we use audio to Mel. So that's our conversion. So let's go ahead and do that. This is going to be our gen audio Mel is equal to audio Mel con dot audio to Mel, gen audio padded dot, or gen audio padded dot squeeze, don't need that extra dimension, and do norm is true. So this is kind of exactly like what we had before. And what I'm hoping is the gen audio Mel looks a lot like, in this case actually, the Mel target. And this is where it becomes important. Remember, this has F max of 8,000. This has no F max, no max, except for like Nyquist. And so this is where it becomes we are basically making the problem a little bit more challenging. We're telling this generator that it needs to generate audio from a Mel spectrogram that has a maximum frequency of 8,000, because this is what Tacotron was trained to do. Tacotron can generate Mel spectrograms up to 8,000. But potentially there are some frequencies that are in this, that are not captured in this Mel spectrogram. They could have been more than 8,000 and were clipped off. And so what we want the generator to do is essentially guess that. If the generator is going to create audio, when I convert back to Mel spectrograms, I want it to include some of those missing frequencies if there were any. And that's basically just a little like making the problem more challenging, right? Making it more challenging. So this gen audio Mel should have frequencies that may not have been present in the original Mel. And basically it's the generator's job to make sure that the audio contains those frequencies. And that's essentially it. Okay, so now that we have that, we can go ahead and do our updates up. So update discriminator. So first we can do optimd.0grad, zero out the gradients. And to do the discriminator is pretty easy, right? So we have our, I'm going to go ahead and copy these in because it's just a lot of typing. Each discriminator, we have two of them. Again, let's look at our multi-scale. They're going to return some outputs. These are going to be the final outputs of every discriminator. Let's look at one of them. X is the final output of the discriminator. Feature maps is all the intermediate outputs and the final output. For training the discriminator, we just need the final output from all the discriminators. So real outs is a stack of all the outputs from the different discriminators, and gen outs is another stack of all the outputs from the different discriminators. These contain all the different intermediate representations as well, which we'll need for generator training, but for the discriminator, we just need these. And similarly, we have the real outs and gen outs for the multi-scale, and in the same way, we had the real outs and gen outs for the multi-period, right? We have both of them. And so all we're doing here is grabbing those. We don't really care about those intermediate representations, so I just ignore them here. We pass in this case, audio and the generated audio to our model.mpd, and then the multi-period. We also pass in the audio and generated audio to MSD. We don't need to backpropagate through the generator. So when we're doing this, we're passing to the discriminator. We're only training the discriminator. So when we backprop, we don't need to backpropagate through the generator as well. So that's why we're doing .detach, because we're only updating the discriminator. We only need gradients on the discriminator, so no need for gradients through the generator, so we detach it. Standard GAN setup. And then we go ahead and compute our discriminator loss, which again was this, right? Just loop through those two, and then make sure that the discriminator thinks that real things are 1 and fake things are 0, using the LS-GAN setup. Good. And so then our total disk loss is just going to be NPD disk loss plus MSD disk loss. That's our total loss. And so then we can accelerator dot backward total disk loss and optim d dot step. Go ahead and do an optimization step. And we're done. That is an update of the discriminator. In the same way, we want to update generator. So let's go ahead and zero out the gradients of the generator, .zero grad. And here's the first one. We want the feature, the Mel Spectrogram loss. We want the Mel Spectrogram of the original data versus the Mel Spectrogram of the generated data to be similar to each other. So reading this, in addition to the GAN objective, we add the Mel Spectrogram loss to improve training efficiency of generator and the fidelity of the generated audio. Referring to previous work, applying a reconstruction loss to GAN models helps generate realistic results. And the time frequency distribution is effectively captured by jointly optimizing multi-resolution spectrograms and the adversarial loss function. And they also see that there's a benefit in the final perceptual quality. Now, here's the interesting thing. How does this work? I generated something, but then I convert it to a Mel spectrogram. How can I backpropagate through that process? Well, actually, we can, and that's what makes this really, really neat. In our dataset, this whole process of audio to Mel, let's go right here. When you take audio and convert to Mel, what are we exactly doing? We are first doing a short-time Fourier transform. Short-time Fourier transform is just a normal Fourier transform applied to different chunks of the data. Fourier transforms are differentiable because it's just a projection. Then we're doing a spectrogram, which is doing the finding the magnitude, torch.abs. Well, ABS, the absolute value, is differentiable, right? Meaningfully differentiable. Going from spectrogram to Mel spectrogram is just multiplying by a weight matrix. Multiplying by a weight matrix is differentiable. Converting from amplitude to decibel, well, that's just logging and multiplying by a constant. Logging and multiplying by constants is differentiable. And normalized is just rescaling the data. And this is also differentiable. So everything you see here, every step here is differentiable. So if we take audio, which has gradients, right, because it came from the generator, and goes through all of these steps to get the Mel spectrogram, and then we compute the loss between the generated Mel and the true Mel, then we can backpropagate through all of these steps too, because everything here is differentiable. And that's a really neat little detail, but I really appreciate that. So that's fine. And so let's go ahead. Our loss Mel is going to be f.l1 loss between the Mel target and the gen audio Mel. And we're going to multiply it by args.lambda Mel, right? And they use 45 because this is actually a pretty small number. So we need to just scale it up in magnitude so it's comparable to the other loss values. That's it. After that, we kind of do exactly what we had before, but this is going to be pretty simple. We need to do our feature loss. So this is the Mel loss. That's Mel spectrogram loss. Now we have our feature matching loss, right? Feature matching loss. And that's pretty straightforward. We have our feature maps from the multi-period discriminator for the real and fake images. We have the feature maps from the multi-scale discriminator for the real and generated images. And so let's just apply our feature loss. And that is just this, right? We know that each of these things here are a list of lists, right? The initial list being all the discriminators and the internal list being the convolution outputs from each of the convolutions in each of those discriminators. And that's exactly why we wrote this, right? There's a double for loop, one through the discriminators and one through each output of each convolution in each of those discriminators. And so yeah, we can just go ahead and compute our feature losses. No problem there. And then we have our generator losses. So I'll keep just pasting these in so I don't have to type them in. We have our generator losses. These are the logits of the output generations from the multi-period and multi-scale. And our generator needs to update in such a way that the discriminator thinks that these are real. And so we just flipped them around. That's the generator loss. It's just doing exactly the opposite of the discriminator loss. And so there you go. That is our generator loss. And so our total gen loss is just going to be MSD gen loss plus MPD gen loss plus MSD feature loss plus MPD feature loss plus the loss Mel, right? The final loss Mel right here. And so then we can go ahead and just update our model, right? Accelerate it backward, update, and we are good to go. After that, we just have a bunch of little housekeeping, logging, stuff like that. So first, every once in a while, go ahead and print to console. If every once in a while, go ahead and log to weights and biases. And after all of that, we've completed a step. And this is one epoch. After we've completed a singular epoch, we can go ahead and evaluate. And the evaluation script is no different, so we can just paste all of this stuff in. There's nothing new here. Basically, in every evaluation, loop to the test loader, and all we're going to do is compute the Mel loss, and that's it. We just want to compute the Mel loss and just keep track of how is the Mel loss doing, basically our Mel reconstruction loss, this one right here. How's it doing on the validation set? Because it's the only thing that's meaningfully interpretable when it comes to GANs. All the other loss values don't really mean anything. We just want to see them do something. So there we go. We're going to go ahead and store them, compute them, and then every once in a while, we're going to go ahead and print it out, log, wait for everything to finish, throw the model back into training mode. Every once in a while, checkpoint the model. At the end, we've completed an epoch, update our schedulers, print out that we're updating our learning rate, and then go ahead and save the model once we're done. And that's basically it, right? There's not really a lot going on in this training loop. And so what we should see if we run this, so I already have a train.sh right here. This will go ahead and train the model, right? So let's go ahead and try that out. Bash train.sh. See if we have any bugs that we need to solve. Okay, let's see right here. Config.upsample channels. Looks like I have a upsample initial channels. So let me go back to the model and just have a spelling mistake. It's channel. There we go. I think that should fix it. Let's see now. Right, so our effective upsampling rate is 256. And there we go. We're now training. And, this'll do its thing. Okay, so after you've completed training this for a sufficient amount of time, these models actually take quite a bit of time to train. Maybe a couple days to maybe 7-8 days, depending on what kind of resources you have. Yeah, they're not really fun to train. You're better off just grabbing one of the pre-trained ones that they offer in the HIFIGAN Git repository and just using theirs, right? But either way, you can train this, but like I mentioned, after training this model, that's only good to take true Mel spectrograms and project them to audio, right? Basically take true Mel spectrograms and create audio out of them. That's not as helpful. So what we do, and this code is basically from what we had in the Tacotron video, so I'm not going to type it again. Basically, what we're going to do is loop through our data, our actual data, and then inference our TTS dataset. So what we're doing here is loading our Tacotron model from what we trained earlier. And then all we're going to do is, as we loop through our data loader, inference them. Inference our Mel spectrograms out of those Tacotrons, basically the Mel postnet out, the final output. and then store those outputs as a NumPy file. So these are going to be true these are going to be the generated Mel Spectrograms from our Tacotron. So that essentially is this, right? Produce some of these from Tacotron. And then fine-tune our HIFIGAN to take these, instead of taking true Mel Spectrograms, take the Tacotron-generated Mel Spectrograms, and then produce the corresponding ground truth audio from there. So it's a little bit different, right? But this is, again, what we wrote that extra chunk of code for, right here in the dataset, right? We want to make sure that we first pre-train on true audio Mel Spectrogram pairs, but then fine-tune on generated Mel Spectrogram true audio pairs. Just so that helps, that we kind of cross that small domain gap, just in case there was one. The training script is obviously identical. Nothing changes in train. The only thing that does change in train is this. In the Mel dataset, we're going to have args.finetuning is true, right? Because we're going to be fine-tuning now instead of pre-training. And then in our checkpoint here, we're going to load that pre-trained HIFIGAN model. And that's basically it. That is HIFIGAN. Let's kind of take a quick look at the results here. So here, Tacotron you could find here, pre-training. I think it's, oh, no. So that's fine. Let me find the, did I not put a link? I may not have. All right, let me pull that up real quick. I just want to take a look at the weights and biases results for HIFIGAN. HIFIGAN. Here we go. All right, here we go. So this is what the training looked like for HIFIGAN. Each of these, I forgot exactly what I trained them on, but each of these took about 2 days. This was trained on a 4x840 node. So it's not like a super GPU, but it took about 8 days to get through about 550,000 steps, which I think was about halfway point. Like I didn't actually train for the full 3,100 epochs because it would have just taken too long and I didn't want to wait. But yeah, so we trained for, about almost 2 million iterations actually. So I didn't go all the way. I think this is 2,000 epochs, something like that. I can't remember. But you can see the val-mel loss fell to kind of 0.239. Once this hits about 0.21, then you will actually hit state-of-the-art, like what HIFIGAN, I believe, published in their repository. So we can pull up the, here, I'll pull that up right now. So HIFIGAN repo. So yeah, you'll see that they get close to like 0.21 something, right? So that's the arc, but you have to train for a little bit longer to get there. Training is otherwise pretty straightforward. You just have to wait. These models take forever because, again, the alignment between the Mel spectrogram and that missing phase information to the actual audio is quite a bit challenging. So training takes forever. Inference is pretty quick. These models are nice because it's just a lightweight convolutional neural network, right? So we can inference them pretty quickly, which is why, again, they're pretty popular compared to like other autoregressive based methods that do a lot of the same things. Okay, so that is essentially HIFIGAN. Let me do a quick recap of the results here, and then we'll listen one more time. So let's actually listen first, and then we'll look at the results. So like I mentioned, let's do a recap. This was the original Griffin-Lim audio.
He had been in the employ of a corn chandler.
Right? And then HIFIGAN sounds quite a bit better.
He had been in the employ of a corn chandler at Islington.
Right? So, I mean, it's not perfect, but it's meaningfully better than just Griffin-Lim. Now, what we want to do is the full pipeline. We want to try it with our Tacotron model. So I've loaded the Tacotron model here and the HIFIGAN model, both the HIFIGAN and the fine-tuned HIFIGAN. And how this pipeline works is pretty easy. We provided some text, and Tacotron produces a Mel spectrogram given text tokens. And then Griffin-Lim can undo that, right? Project it to audio, or we can use HIFIGAN or the fine-tuned HIFIGAN to do exactly the same thing. So you go ahead and just do HIFIGAN.generator, pass it the output, which is our Mel spectrograms, and then just convert them back to audio, right? Just like play them back. So what I've done here is I've provided the phrase that we had earlier, right? And let's just listen to them. I need to run you. run U, and run U. That should be everything. Okay, so this is the generated Mel spectrograms from our HIFIGAN, or from Tacotron. So let's just listen to them. Griffin-Lim, this is that same phrase as before, but now, instead of passing in ground truth, remember this one here, this is ground truth Mel spectrogram from the actual audio. This is generated from a TTS system, Tacotron system, and then on that we do our Griffin-Lim. So instead of ground truth spectrograms, this is a generated spectrogram.
He had been in the employ of a corn chandler at Islington and went into London with his master's cart and horse.
Okay, sounds pretty good, but Griffin-Lim has its limitations.
He had been in the employ of a corn chandler at Islington and went into London with his master's cart and horse.
Okay, so that
He had been in the employ of a corn. He had been in the employ of a corn.
See, that's meaningfully better. You can hear it, right? So that's good. Let's see what the fine-tuned one is. So this was just trained on pre-training data. This was then additionally fine-tuned afterwards.
He had been in the employ of a corn chandler at Islington and went into London with his master's cart and horse.
Okay.
Corn chandler at Islington and went into London with his master's cart and horse. Employ of a corn chandler at Islington and went into London with his master's cart.
So you might be able to hear, maybe listen to the Islington part very clearly.
He had been in the employ of a corn chandler at Islington and went into London with his master.
So here where it says and went in.
And went into London.
You hear like that robotic echoey sound. Let's hear it here again.
Islington. And went into London with his master's cart.
That artifacting no longer exists in the fine-tuned one, right? And that's why, like I mentioned, there's going to be a little bit of a domain discrepancy. And so we'll hear some improvements to generative performance by just doing a little bit of fine-tuning, right? And that's pretty standard. Let's try a phrase, again, this is in sample. Let's try a phrase that definitely wasn't in the dataset. Artificial intelligence is awesome.
Artificial intelligence is awesome.
Okay.
Artificial intelligence is awesome.
Okay.
Artificial intelligence is awesome.
We can hear, because this is more out of domain, there's less of a difference here, right? Because again, there's a limitation on Tacotron, because Tacotron's probably never seen some of these words, or they've never seen these words strung together in this way. All right, we can try something else. Let's try deep learning is the future of, I don't know, science, whatever. Let's listen.
Deep learning is the future of science.
Okay.
Deep learning is the future of science. Deep learning is the future of science.
Okay, good. So it's, it sounds like what it's supposed to say, but it's not that good in kind of out of domain speech. And so this brings us to a couple of things. Number one, speech models like this are typically not as popular these days for a couple of reasons. One, you can hear that the intonation or the prosody, the kind of acoustic, the way that they're saying it, right? The way that this TTS system is saying it doesn't exactly sound natural, right? And how we define natural is actually quite a bit more challenging. This is why a lot of models today do more than just what we did here, generate a Mel spectrogram. There's going to be variance predictors, there's duration predictors, there's phonemes with like graphing to phoneme modules. There's all sorts of additional mechanisms built in to make TTS systems sound more natural. And that's not something that Tacotron, because again, Tacotron is a pretty early architecture. This is mostly a Tacotron limitation. HIFIGAN is still as good as ever, right? HIFIGAN is great at taking Mel spectrograms and producing audio, and that's why it's used in all over the place. Another class of models that's become more popular lately are speech LLMs, where we are essentially doing something called speech tokenization, where we convert audio to discrete codes. If you watch my Wave2Vec video, you already have an idea, or the VQVAE, Vector Quantized Variable Encoder video, and the Residual Vector Quantized Variable Encoder video, you already have an idea of this, but basically training a big speech tokenizer on audio, and then following it up with training those tokens on giant LLMs has become even more popular these days. As a quick example, I'll show you encodec. Right, encodec is something that I'm working on and hopefully will be able to implement for y'all one day, a live implementation. But you'll notice something a little bit here. We have kind of the same setup. We have a encoder, decoder, and a discriminator, or a couple of different kinds of discriminators, multi-scale discriminators, what they call it. So this entire idea of having like multiple different types of discriminators and that sort of stuff shows up all over the place. And so there's a lot of really cool work to do still in the TTS space that I will be working on. Hopefully we'll try to do fast speech or something like that first, just to kind of, or maybe like a normalizing flow-based speech model. I haven't decided yet. There's a bunch of stuff that I want to try. But for now, I hope this made sense. HIFIGAN, again, this is a neural vocoder. Vocoders take some intermediate representation and produce actual audio. Vocoders have actually existed for a long time, but essentially now we call them neural vocoders. Vocoders are like, they've existed since the early 1900s, like for like voice codecs and telecommunications and things like that, where you can like encrypt audio and then decrypt it again, and that sort of stuff. So there's lots of really cool work to come, or really cool work that we want to do in the future. For now though, that is the end of the HIFIGAN implementation. So I will see y'all in the next one.